So now I can show you how to convolve two cauchy random variables. Theorem: cauchy of bx and ax convolved with cauchy of by and ay is cauchy of parameters bx plus by and ax plus ay. And by now everybody is familiar with this convolution notation. It just says if I take a cauchy random variable of parameters bx, ax, independently another cauchy of parameters by, ay, add them up, the sum is going to be cauchy again with parameters bx plus by and ax plus ay. Before proving this, if you remember, if I bring back the picture kind of definition of cauchy, so it's just the position of the light beam at a uniform angle. And if anybody knows the Huygens principle from wave propagation in physics, then this is actually not a surprising fact. So if anybody is interested and has some physics interests, then you can derive this from just the Huygens principle of wave propagation in physics. It's actually quite easy to see that this has to be the case. But we're going to do this now with the probabilistic formulation and of course the convolution formula, and we are going to use the residue theorem. So let's prove this, and again I'm going to do it in two steps. Case 1, let's assume that the b's are 0. bx and by are both 0. I cannot assume that the a's are 0, but let's assume that. And we've seen this kind of strategy with the normal random variables where we assume that the means are 0. And I also told there that the sigmas, one of the sigmas could be transformed out but not both. And it's the same case here. One of the a's I could transform out if I wanted to, but not both. I am not going to transform them out, so I'm going to do the full thing with b is equal to 0. Okay, so what is the convolution of these two cauchys? So x will have this distribution and y will have the other. What is the convolution at z? It is by definition, or by the, not the definition, but by the formula we found for convolution, it's one of the densities, say the one of x, taken at z minus y. That's the cauchy density of x taken at z minus y, times the other one of y taken at just y, integrated out. And these densities are valid on the whole real line, so I don't need to bother with the integration boundaries. It goes from minus infinity to infinity. Okay, now this is not a nice integral. It's, again, to do it in closed form is not obvious how to do it. So we're going to go to the complex word and we're going to find the complex way of doing it using the residue theorem. The first thing to notice is that while this behaves perfectly nice on the real line, as soon as we go out into complex with y, we are going to have some blowups. If y squared plus ay squared is 0, or if z minus y squared and ax squared is 0, then we're going to have some problem here. So there is going to be some poles of this function. Outside those poles is just a fraction of polynomials, so it's a nice rational polynomial fractional function, and there's no problem with that. But at those particular points where ay squared plus y squared equals to 0, or ax squared plus z minus y squared equals to 0, at these points we're going to have some issues. So let's find these points actually. What are these points explicitly? Well, this tells us that y is going to be plus minus I a y, and this tells us that, well, let's do it this way, y minus z is going to be plus minus I a x. Okay, just rearrange this. inside this square, it doesn't matter if it's z minus y or y minus x. I move it to the other side, that's what I get. And so this means that y is going to be z plus minus IAX. These are the poles, so we have 4 poles, and we need to take care of them. Okay. Now what I'm going to say from here on is assuming that these poles are different. So strictly speaking, if z is 0 and AY equals AX, then what I say is not true. Then the below is not valid. Notice that z is real, right? We're plugging in a real number to the convolution. So the below is not valid, because then these poles actually coincide, and we're dealing with a second order pole. However, it's just one number in the density, and within a density we never care about a single number. If we integrate a density, which we always do with densities, a single point doesn't matter. So from now on, I'm going to assume that it's not the case that both AX equals AY and Z is 0, but even if AX equals AY, it's only just one point in the density. It's not a big deal. Okay, now once we figure this out, then let's rewrite the integral into a nicer form. So we are going to look at the integral, actually the integrand itself. So I'm going to rewrite the first one, so this bit and this bit together. I'm going to rewrite as soon as you find out the roots of a polynomial and you find out the coefficient of this leading term, then you can write this as y minus z minus the first root, which is z plus IAX, times y minus the other root, which is z minus IAX, but because it's another minus, it's going to be a plus. So this product here is going to give me back AX squared plus z minus y squared. And in a similar way, I can write the second factor, AY over A squared plus y squared, as y plus AI and y minus AI, IA. Let's start with the plus here. So when I have the pole at IAY, then I subtract that and get this term. When I have the pole at negative IAY, I again subtract that, but this becomes a plus. So I have that term. So this denominator can be written as that product. If you don't believe it, just multiply it together and you'll see. That's one way of writing it. And then there is another way of writing it, which I am also going to use. It's just a very simple change. I am going to swap the minus sign into both of these terms. And if I do that, then of course nothing is going to change. So I'm going to say it's going to be z minus y plus IAX. I factored in a minus sign here. And I factor out another minus sign there, z minus y minus IAX for the first term, and for the second term is going to be, I just keep it as it was, y minus IA and y plus IA. Okay, and of course I is the complex unit. I didn't say that, but I think that's obvious. All right, now let's calculate the residues. So this is my integrand apart from 1 over pi. I am going to call this actually f of y. This is f of y. So let's find the residue of this whole business. So this is f of y. What is the residue of f of y at these particular points? Now, in fact, I am only going to consider, and we'll come back to this a bit later, I am only going to consider the poles at the positive imaginary bits, so positive IAY and positive Z plus IAX. So at y equals IAY, and I'm going to also to do that at y equals Z plus IAX. You'll see later on why I'm only doing that. Okay, so what is the formula? The formula I told you about in a previous video tells us that if this is a first order pole, which it is, because at IAY this is the only term which is going to 0 in the denominator, so there is only a first power of 0, if you wish, a linear way of going to 0 in the denominator. So this is the first order pole. In that case, I just multiply by the independent variable minus the position of the pole, my whole function, which is essentially just cancelling out the troublesome term, and take a limit at that point of the other terms. So it's actually very easy in this first order case. The residuum at IAY is going to be, that single number, is going to be that function, and I'm going to use the second bit for that, this function here multiplied by y minus IAY, which will kill off this term, and plugged in y equals to IAY. So it's actually quite simple. AX over Z minus IAY minus IAX for the first term. So I just plugged in IAY here. Z minus IAY minus, oh sorry, this was a plus here, now it's a minus, IAX, okay, then AY over, so now remember we have to multiply with y minus the position of the pole, our function, and that exactly kills off the term which we have a problem with, so I don't have that one. And I have IAY for y here, plus IAY again. So that's the only term that survives. Okay, let's simplify this a little bit. AXAY on top. And then on the bottom, I want to write this as Z minus I AY minus AX in a parenthesis for this first one. Then maybe I should start a new line. Let's start a new line for this. So AX over Z minus IAY minus AX. These together will give me the plus IAX. And then Z minus I AY plus AX. That's this term. And then here, it's actually quite a simple thing that happens. It's just going to be 1 over, well, AY over 2I AY. So that is just going to give me a 2I down here. So that term just gives me 1 over 2I. Okay. Now for the second one, let's do the residue of Fy at the other pole, namely Z plus IAX. Okay. What is this? Well, the idea is pretty much the same. I am going to use this form, this first form of it. It's going to be a little bit simpler. And all I need to do is cancel out, forget about the y minus z minus IAX term, because this is the one that's going to blow up, and this is the one which is cancelled out by doing the residue. Okay, so I'm cancelling, forgetting about this term, and write down all the rest with y equals to this point instead. when I do that, then I end up with y minus z plus iax at this point for y. The z's cancel, so I just have iax and another iax, and that's all that's left from the first term. At the second term, I'm just going to plug in whatever I have there, so it's z plus iax plus iay, and then z plus iax, this was a minus, sorry, this was a minus here, this is going to be a plus, okay, and that's all I have here. Again, I want to write this slightly simpler, so the ax cancel here, and I have just a 1 over 2i, and I have, well, let's write this straight away as ay over 2i, and then these guys, so z minus I ay minus ax, that's for the first term, and then z plus I ay plus ax, that's for the second term. So these are the residues at these two different points. Okay, so now that we have this preliminary calculation, now we can actually do the contour integral. We can calculate the integral, and that needs a little bit of thought about our curves. So what do we need to do? So again, the convolution at z, where z is now a real number, is going to be a 1 over pi squared that's coming in front, and then an integral from minus infinity to infinity of fy. This is what we called, it's probably not a very good idea to call it f, but anyway, so this is what we called f, right? This is what we called f, fy dy. Okay, now here is the deal. First of all, I have the right to write this as a limit as r goes to infinity of an integral from minus r to r of my function. This is a nice integrable function. It's clear that this is integrable because it decays like 1 over y square times 1 over y square. So this is a very nice decay. There is no problem with that. And then the infinite integral exists fine, and I can just write it as the limit of the finite integrals from minus r to r. And now I'm going to tell you what my curve gamma is going to be. So gamma is going to be the curve of a segment from minus r to r, and then a semicircle going around the origin in the positive direction. So I'm going to go around like this. And now I'm going to say that if I look at the integral along this gamma of my function, and let's just carry the 1 over pi square with us. This has of course two contributions: the integral, the real integral from minus r to r, which is this segment here, and the integral of 1 over pi square on the semicircle, the complex line integral on the semicircle only. Okay? This bit is the one I'm interested in. This bit is the one I can do with the residue theorem because I have a closed nice curve. And this bit I'm just going to show you that this goes to 0. So why does it go to 0? Because again, if you look at fy, it has essentially 1 over y square and 1 over y square with some constants in front. For large y's, if y mod is r, which it is on the circle, we're on the semicircle here, So the absolute value, the complex absolute value of y is r, and r is going to be large, so I'm taking this large. Then y, f of y essentially behaves the mod of f of y, so let's do it this way. Mod of f of y is behaving like 1 over r to the 4. So this function that I'm integrating on the semicircle is in the order of 1 over r to the 4. The semicircle has length pi times r. Okay? The semicircle has length pi times r. So if I integrate something of the order of 1 over r to the 4, and I'm integrating this over the length of pi times r, then in order of magnitude, it's going to be r over r cube, r over r fourth, which is 1 over r cube. So this will go to 0 as the cube of r, the reciprocal of the cube of r, as r goes to infinity. Okay? So when I take a limit, it's enough to look at the limit of this contour integral along this closed curve. And that's where the residue theorem comes in. The residue theorem tells me that as soon as r is large enough to include some of my poles, actually all of the poles which it's ever going to include, namely the ones on the positive semicircle, the positive half plane, the positive imaginary part, the plus iay and the z plus iax, these guys are somewhere here. The a is positive, right? So these guys are somewhere here. iay is here. Z plus iax is there. Z is a real number. As soon as r is large enough to include those, then the value of this contour integral will not change anymore. It is just going to be the sum of these two residues. That's the residue theorem. Okay? The sum of the contour integral is only taking a contribution from the residues, and so this is going to be, this thing is going to be 2 pi I, the residue of f at y equals to iay, and let's not forget about the 1 over pi square, and the residue of f at the other pole, which was z plus iax. Again, let's not forget about the 1 over pi square. So the two residues were iay and z plus iax. So these are the two things I'm taking here. And these have been calculated. These have been calculated in the previous page. So the first one is here and the other one is there. Oops, there. Okay. Before I actually write them in, I am going to slightly rewrite them, and I'm going to call this bit here, I'm going to call A. I'm going to call this bit there B, and then I'm going to notice that this one here is again A, and this one here is almost B except for the sign change in front of I. Notice that the A's are real. The sign change for the complex part gives me a complex conjugate of B. So this is a complex conjugate of B. So I'm going to say that here I have AX over 2iAB, and there I have AY over 2iA and the complex conjugate of B, where A and B are the things here. So let's see what happens if I add these two up. So I have 2 pi I, and an over pi square. Okay, we're going to simplify with the pi in a second. But let's do the first one. So AX over 2iAB. And then here I have the 2 pi I over pi square again. and then the other one ay over 2I a and the complex conjugate of b. Okay, so what is this? What is this? Okay, now I'm really simplifying with the pi and also with the 2i, so I have a 1 over pi in front. The 2i's are gone and all the other pi's are gone, and I want to make this into a common fraction with common denominator a, b bar, right? A is common, b and b bar are going to be down there, and then I get ax b bar plus ayb. Okay, now it's time to plug back in what a's and b's were. 1 over pi, and then let's start with downstairs. So I'm going to write in A, which is z minus I a y minus a x. That's A. Now, what is B complex conjugate? B and B complex conjugate is, of course, the mod square of B, and that's just the square of the real part plus the square of the imaginary part together. So that's gonna be, for B, z square plus the square of ax plus ay. This is b bar, or the mod square of B. Real part, imaginary part squared, added together. Okay, and then I need to put here ax times b bar. Here is b bar. So z plus I a y plus ax. And I have to add ay times b, which is z, and b is there, minus I ay plus ax. This is what I have. And now the thing to notice is that I actually can factor out, an ax plus ay from here and from there. And I can actually also factor out an ax plus ay from the z. Okay? So I'm going to treat these terms separately. I'm going to have z times, I'm going to have z times ax plus ay, and this comes from these terms. Okay, and then I'm going to have a ay plus ax separately, and ay plus ax separately. One of them is multiplied by iax, and that's this term, iax, the sum. The other one is multiplied by negative iay, so negative iay, and that's all I have on top. And on the bottom I have the same thing as before, z, and I'm going to break up this parenthesis now. So z plus iax minus iay. That's my first term. The other term is z plus ax plus ay, and both separately squared. That's the second term. I don't need this one anymore. And so now I notice that I can just cancel out with these guys. This is never 0, right? Because z is real, and okay, I assume that z and ax and ay are not ax and ay are not 0 at the same time as z equals to 0. So I can cancel these out, and then I'm done. Then I arrive to 1 over pi ax plus ay over z square plus ax plus ay square, which is exactly the Cauchy distribution, Cauchy density actually. It's exactly of this form, fx equals to a over a square plus z square, except for a I'm using the sum, and that's exactly the Cauchy density. So this is going to be the Cauchy density of parameter 0 for the shift parameter and ax plus ay for the height parameter at z. So I conclude that x plus y has this distribution, Cauchy of 0 ax plus ay. Okay, so that concludes case 1. That concludes the case when bx equals by equals 0. Let's then do case 2, and the idea is the same as what we did with the normal variables, that namely I can transform out the horizontal shift parameter. So let's do case 2 for general Cauchys. Case 2, if we have Cauchy of bx ax convolved with Cauchy of by and ay, okay, then the idea is again using the nice transformation properties of Cauchy, namely if we multiply a Cauchy of some parameters with some number c and shifted by some number d, we again get a Cauchy where the first parameter transforms as cb plus d and the second as c times a. Now I don't care about c for this proof, I'm just going to shift things, so I'm just going to add these. Namely, I want to make these into Cauchy 0a. So take x with this distribution and y with that distribution, and of course they are independent of each other, and try to find out about the distribution of their sums. So now if I pick c equals to 1 and d equals to minus b, then I get a 0 parameter at front. So let's subtract b from both. And then of course I have to add these b's back, bx and by. Okay, now case 1 applies to these people, because according to the previous sheet, which I shouldn't have taken away, if I do d equals to minus b and c equals to 1, then I end up with okay, d equals to minus b, that's exactly what I did here, c equals to 1, exactly what I did here, then I end up with the Cauchy of parameters 0 and c equals to 1, so 0 and the original a. So this is going to be Cauchy of 0ax, this is going to be Cauchy of 0ay. Of course they are still independent, so I have to convolve, so there's the distribution, I have to convolve them to find the distribution of this sum. According to case 1, this is going to be Cauchy of 0 and parameters 0 and parameters a's added up. That's what we just found in the previous case. So ax plus ay. And now I'm going to shift it back by adding these constants here. And that will again result in just adding some parameter back there. Actually, that back here. That will just shift the first parameter by that constant. So that will make out of this Cauchy 0 and ax plus ab, it will make a Cauchy bx plus by, namely this constant and the original here ax plus ay, and that concludes the proof that cauchy convolves to cauchy again with both the a and the b parameters added up.